Hello and welcome back to the lecture 5 of this series QM101. Today we will start talking about time evolution and quantum mechanics. So in the past few videos I have covered a lot of stuff. Those lectures were a little too exhaustive, like there were a lot of detail, and the lectures were also a little long. So I'll try to go slower this time and try to cover comparatively little less stuff in a single video. Okay, so let's get started. So before talking about time evolution, I would first like to tell you about normalization of state, and this is something I should have told you earlier, but I forgot to even talk about it. So let's get started with that. So suppose you are given a vector psi in a Hilbert space. As you know that this vector represents a state, a quantum state of a system, of a single particle or multiple particles. Now if you multiply this kit vector psi with a number c, where c is a complex number. Generally we deal with complex number in quantum mechanics, as I've said multiple times. Then this will also become another vector which belongs to the same Hilbert space H. Now what is the physical difference between this psi and c psi? And this is very crucial and very trivial thing, but it's also really crucial, is that psi and c psi, both of them represents the same physical state. So basically there is no difference between psi and c psi. Mathematically, if psi is say 1 then c psi would be cc. So mathematically they are definitely not the same thing, but physically they represent the same thing, so they are equivalent. So if I write it, psi and c psi, they are equivalent states physically, and there is an equivalence relation between them, and this means that what represents a state and is not just a vector, it's a entire array of vectors. Okay, so let me just draw a diagram here. So suppose this is a 2D Hilbert space, suppose. Okay, although this is not like, this is just a pictorial depiction. So suppose this is a vector space, the Hilbert space, and this is a vector which corresponds to the state psi. This is a vector psi which corresponds to some state. I'll just call it state 1, and this yellow vector is the psi. Then if I take another vector which is a just scaled version of this vector, let's call this psi prime. Another vector, say in opposite direction, this is say psi double prime. All these vectors, they correspond to the same state 1. But if I take another vector which is not in this line, which does not lie in this line, say this vector, okay, now I'm getting out of choice for colors. Okay, so suppose this is another vector, let's call this phi. This phi will correspond to a different state, say 2. Okay, this will not correspond to the state in which was represented by these vectors. But if you take another vector, say this vector, a vector which is scaled version of this, or this, basically any vector which lies in this line, then all these vectors will correspond to this state 2. So this line corresponds to the state 1 and this line corresponds to the state 2, and we call this a ray. You can call it a ray, or you can also call it a subspace of this Hilbert space, as one-dimensional subspace. It is this subspace which represents all the states of it is this subspace of the Hilbert space which represents a given state in quantum mechanics. Okay, now here comes the most important part. since since psi and c psi, they both belong to the same, like they both represent the same state, then how do we choose a given psi? Like we generally work with a single vector, not with all the arrays of these vectors. Then how do we choose psi? How to choose? So answer is very simple, and this is what we call, we choose a normalized state. Now what I mean by normalized state, so a normalized state is such a state psi, if you take its inner product with itself, then the number which you get is 1. So this is what we mean by a normalized state. Any vector psi which satisfies this condition is called a normalized state. Now what if you're given a function is a state psi which is not normalized, in the sense that you are given a psi such that you take its inner product and you get some number alpha which is a complex number and is not equal to 1, then you can, if the state is not already normalized, you can normalize it via the procedure of normalization. This is what we call normalization, and it's really simple to normalize a state. You basically, you are given the number alpha, so you define a different vector psi prime using this psi. You multiply this psi with 1 by square root of alpha. Now since alpha was a complex number, then this number will also be a complex number, and when you do multiply with this, now you, since it's a complex number, that means psi prime and psi, they both represent the same quantum state. And since this is the case, that, and when you take this product, inner product of psi prime with itself, you will get 1 as an answer. You can just check it. Okay. So this psi prime is called, it becomes a normalized state, and this number which we multiplied in an unnormalized vector to normalize it is called the normalization constant. So when we are doing quantum mechanics, when we are doing calculations, we try to stick with normalized vectors only. There are some cases where you might need to use some different vector, but mostly we will deal with normalized vectors. Now given normalization, now we can move to the next topic, which is the main topic of this lecture, that is the time evolution. Now let's recall again, what does psi represents? It represents a state, and an operator on, and psi belongs to the Hilbert space H, and O is an operator, that is a map from H to H. This operator represents the observables. So psi state can be like, say, up spin or down spin of electron, and operators will represent measurable quantities like position operator, momentum operator, and energy of Hamiltonian operator, which is the energy, and so on. Now so here's the big question: what does change with time? Is it the state which changes with time, or the observable? You might think, okay, state changes for time makes sense, but observable, like up state, there is an up state, it's called like something like that, because a state is what generally changes with time. In even classical mechanics, the state was represented by the position and momentum and other variables, and it is these variables which changed with time, right? We used to find how does the position change. So in classical mechanics, this was the state, and so changing of state makes sense. But here the position is the operator, so operator changing with time, this also sort of makes sense. So what does change exactly with time? Which of these changes with time? And the answer is both of them can change with time. Sorry, not both, I should say either of this can change with time. What is happening? So you can change either the state or the operator, and the underlying physics would sorry, and the corresponding physics would be the same. Like if you change the state with time, the physics it tells, and which is the operator with time, the physics it tells would be the same. It's just, and since they are the different objects, the rules are different for these two, but the eventually what will you get is the same. Okay, so when you change the state, sorry, evolve the state, this kind of quantum mechanics is called, like this picture of evolving a state is called, what we call Schrodinger picture. And when you evolve the operator, it's called Heisenberg picture. So generally when students learn quantum mechanics, they are generally taught the Schrodinger picture because it's easier to understand, and we will learn this as well. But Heisenberg picture is often used in most of the advanced thing like quantum field theory and so on. Okay, so we'll talk about Heisenberg picture as well, but in somewhere later in this course. Now that we have come all this way, now recall the principle 5 of the quantum mechanics from the video, from I think the second lecture, that is the axioms of quantum mechanics. I said there that I'll discuss this principle later, somewhere later in the video, and now is the time to discuss it properly. So the principle said that the evolution of state vectors with time is unitary. What do we mean by this? So let's start with this. Suppose at time t is equals to 0, we are given a state vector psi, which is I'm calling psi of 0, and it belongs to some Hilbert, to the given Hilbert space H. And if the state is changing with time, then after some time t has elapsed, the state vector will become psi t, and it will belong to the same Hilbert space, because Hilbert space is the possibility, like is the space of all possible quantum states. So this state and this state will belong to the same Hilbert space, but they might not be equal, and sorry, they're definitely not equal, and they might not be equivalent as well. Not equivalent. Okay, so but since they belongs to the same Hilbert space, which is the same vector space, so you can say that there is a vector u 0 to t. This basically represents the time evolution from time 0 to t. I represent it using the symbol ut simply, and this is a map from Hilbert space to itself. It's an operator such that when you take the time psi at 0 and you multiply this operator t, sorry ut, then you get the quantum state at time t equals to t. Okay, so this is the first thing, that there exists such an operator which when you multiply it at psi 0, you'll get psi t. Now here is another thing. What does initially you start with a normalized vector, that is psi of 0, psi is 0 is equals to 1. Now what does this normalization condition exactly mean? This means that total probability of finding the system in the given state. So this one is actually coming from the concept of probability. So let me just elaborate on this. So you are given a state psi. Okay, since I've already written it, it's a little more difficult to make space for the other stuff, but let me try. You're given psi 0 and you want to know what is the state of being in psi 0. It is just like asking that given psi 0, what is the probability of being in psi 0? Obviously 1. It is just like if I tell you that I am in a home and then ask you what is the probability of me being in a home, obviously it's 1 because I already told you I'm at home. Okay, so this is another important thing that you can be used. So this is how you visualize it, why it is 1. Okay, so normalization is basically giving you the total probability, and total probability of being in a given state is total probability is always 1. Like, and this psi does not represent a single state, it can be a superposition of multiple states as well. Remember that. Cn, I mean, I think we'll come to this because I think it might get confusing, but normalization is basically to make sure that the total probability is 1. Okay, I think that makes more sense. Normalization is to ensure that the total probability is 1. Now if the total probability at time 0 is 1, it should remain 1 only at time t as well. So that means psi t in the product should also be 1. Now that means these and these are the same thing. So psi t and psi 0 in the product, they are the same. And now when you write psi t in terms of psi 0 using this equation, you get this expression. And here psi 0 in between you have u dagger t ut, and here you have in between there's nothing, so that means you can write it as psi 0 identity operator psi 0. What is identity operator? Identity operator 1 is a map from Hilbert space to Hilbert space such that any vector psi is mapped to itself. That is what we mean by identity operator. And when you take this on this side, you can write it like this: psi 0 u dagger u minus identity operator psi 0 is equals to 0. Now this u dagger, I didn't write the t here, but it is like implied that there is the ut. It's the ut, not just u. Now this quantity needs to be 0. What does that mean? So it eventually it implies that u dagger ut is 1, but this you cannot, like, just looking at this you cannot conclude this. Why? So let's get back to a little bit of linear algebra. So there is this theorem, I mean, it can be proved really easily, that if you are given a vector, x is a vector and m is a matrix representation of, say, of a map from vector space V to V, then this quantity x dagger, so sorry, I am messing it up here a little. So x is a vector, let me just write it in terms of bracket. X is a vector, m is an operator, x is its corresponding dual, then x equals to 0 implies that m dagger is equals to minus m. Yeah, I think writing like this makes more sense. We should stick to a single notation. That means m is an anti-Hermitian matrix. So this means that u dagger u minus 1 is an anti-Hermitian matrix. This statement can be proven easily using linear algebra. Okay, and maybe you can just use it using matrices. Also, this thing is generally a matrix M can be anti-Hermitian, but this given matrix u dagger u minus 1, you can just check it simply using the properties of this dagger, that u dagger u minus 1, when you take the dagger, it is same as this thing. Now since this is, if you think of it as m, this is equals to minus m, this is equals to m as well, that means m has to 0, that means this quantity has to be 0, and since this quantity has to be 0, that's why u dagger u is equal to 1, sorry, identity operator. And this condition is what we call unitarity. So an operator which satisfies this property is called a unitary operator. That means the time evolution operator. So time evolution operator is a unitary operator. And what does unitarity implies? It implies that probability is conserved under time evolution. So again, I think the lecture got a little lengthier because there was like a lot, I messed up the explanation at a few places, but I hope you liked the video, so, and you learned something. So remember all this, like if you didn't understand any part, you can just go back to it. I have I agree that my explanation was not really good, but I have told everything in the video which was needed to be said. Okay, so with that I just end this lecture, and we'll talk about more about on this unit time evolution operator in the next video as well. Okay, so till then, see ya. Also, as I keep forgetting, if you like the video, please press the like button and subscribe to the channel for upcoming videos, and I'll see you guys in the next video. Bye bye.